Tonight, we're going to travel to the edge of the universe, not the edge of our solar system, not the edge of the galaxy, or the faint smudge of the farthest thing a telescope has ever caught on a clear night. The actual edge. The farthest point there is in every direction you could ever choose to look. You probably picture the edge as a kind of wall, a boundary, a place where the stars thin out and stop. And beyond it, maybe nothing, whatever nothing would even look like. That's the natural thing to imagine. It's almost certainly wrong. It sits about 46 billion light years away, and it sits exactly that far away no matter which way you turn, left, right, up, straight down, through the floor and out the other side of the world. You are, right now, sitting at the center of a sphere 46 billion light years across. So is everyone else. We'll come back to how that's possible. But here's the thing most people never realize. The edge of the universe isn't a place at all. It's a moment in time. And the thing that's waiting out there, the actual material at the end of everything, the stuff the edge is physically made of, is the oldest light in existence. Light that has been traveling toward you for 13.8 billion years and is only arriving now, tonight. While you lie here, it is still glowing. It has never stopped. By the end of tonight, you're going to understand exactly what that light is, where it came from, and why, if you could stand at the edge and look at it directly, it would not be black at all. It would be on fire. Before we drift out there, if these slow journeys through the cosmos are where you come to quiet your mind at the end of the day, take a moment to subscribe and follow along. It's a small thing, but it's what keeps these long nights of space and stillness going. Now, let's begin. Let's start with the word itself, edge. When you say the edge of a table, you mean the place where the table stops and the air begins. There's a table, and then there's not table, and the edge is the line between them. That's what the word does in ordinary life. It separates a thing from where the thing ends. So when people ask, what's at the edge of the universe, that's usually the picture in their head. Somewhere very far away, the universe stops. And the question feels like it should have an answer you could walk up to and touch. The trouble is that the universe almost certainly does not have an edge like that. Not a rim, not a wall, not a last galaxy hanging at the border with darkness past it. As far as anyone can tell, space simply keeps going. It may go on forever. It may curve back on itself in a way the human mind was never built to hold. What it almost certainly does not do is end at a surface, the way a table ends. So when an astronomer talks about the edge of the universe, they mean something much stranger and much more specific. They mean the edge of the part we can see, the observable universe. And that edge is real, it's measurable, it has a distance, a temperature, even a color. It is, in every sense that matters, the wall at the end of the sky. It's just not a wall made of matter. It's a wall made of light and of time and of the simple fact that the universe has only existed for so long. Here's what that means. Light is fast, but it is not infinitely fast. It crawls across the cosmos at a fixed speed, about 300,000 kilometers every second. That sounds instant. On the scale of the universe, it is agonizingly slow. Light from the sun takes 8 minutes to reach your eyes. Light from the next nearest star takes more than 4 years. Light from the center of our own galaxy left on its journey 26,000 years ago, when there were still mammoths. Now stretch that out. The universe has a beginning. It switched on in the event we call the Big Bang 13.8 billion years ago. That's not a guess. That's a measured age, and we'll see tonight exactly how it was measured. The point is that the universe has a finite age. It has been running for a specific amount of time, and not 1 second longer. And that puts a hard limit on what you can possibly see. Think about it slowly. Light needs time to travel. The universe has only been here for 13.8 billion years. So, the most distant thing whose light could possibly have reached you by now is a thing whose light has been traveling for almost that entire span, for nearly the whole life of the universe. Anything farther than that, the light is still on its way. It hasn't arrived. It won't arrive for a very long time, and some of it will never arrive at all. That's the edge. It isn't where the universe stops, it's where our view stops. It's the distance light has had time to cross since the beginning. Beyond it, there is almost certainly more universe, more galaxies, more light, more of everything, but we are sealed off from it, not by a barrier, but by time itself. The light just hasn't had long enough to get here. Astronomers have a quiet, almost gentle name for this boundary. They call it the cosmic horizon. And like the horizon out at sea, it isn't an edge that exists out there in the water. It's an edge that exists because of where you're standing and how far you can see from here. Walk forward, and the horizon moves with you. The sea doesn't end at the horizon, your sight does. The cosmic horizon works the same way. It is the farthest light can have come. And that is the only edge the universe has to offer. Now here is where it starts to get strange, and where the edge starts to become something other than just a faraway place. Because light is slow. Looking out into space is the same thing as looking back into time. There is no way to separate the two. When you look at something far away, you are not seeing it as it is. You are seeing it as it was when the light left it. You are always looking at the past. You have never, in your entire life, seen anything in the present. The sun you see is 8 minutes old. If the sun vanished right now, you'd have 8 minutes of ordinary daylight before the sky noticed. The moon, a little over a second. The person across the room, a few billionths of a second, close enough to call now, but not quite. Light always charges you a fee in time, and the fee grows with distance. So, a telescope is not really a distance machine, it's a time machine. The deeper it sees, the further into the past it looks. Point it at Andromeda, the nearest big galaxy, and you're seeing light that left 2.5 million years ago. You are seeing Andromeda as it was before there was anything you'd recognize as a human being. Point it deeper, at galaxies hundreds of millions of light years out, and you're watching a universe that existed before there were flowers on Earth, before there were dinosaurs, before there was complex life of any kind. Keep going. This is the part to hold on to tonight because everything else depends on it. The farther out you look, the younger the universe you are looking at. Not older, younger. It feels backwards, and it takes a moment to settle into place. The most distant galaxies are not ancient, worn-out things. They are the opposite. They are infants. Their light is old. It's been traveling almost the whole life of the universe to reach us. But it shows them as they were, when they were brand new, because that's when the light left. The James Webb Space Telescope was built almost entirely for this one purpose: to look far enough out, and therefore far enough back, to catch galaxies as they were forming in the first few 100 million years after the beginning. And it has. It's found galaxies whose light set out more than 13 billion years ago, when the universe was a small fraction of its current age, clusters of newborn stars blazing in a cosmos that had barely begun. So picture the journey outward as a single continuous fall backward through time. Nearby, the universe looks like home. Mature galaxies settled into graceful spirals turning slowly. Push out, and the spirals get rougher, more chaotic, still being assembled. Push further, and the galaxies break down into clumps and fragments, raw material that hasn't finished becoming anything yet. Further still, and even those thin out, until you reach an era with no galaxies at all, no stars. The universe before it had lit a single light. Astronomers call it the cosmic dark ages, and the name is literal, a stretch of hundreds of millions of years when the cosmos was full of gas and utterly, completely dark. And you're still not at the edge. Keep falling backward, past the dark ages, toward the very beginning. And as you do, the universe you're looking at gets smaller, hotter, denser, brighter. It's shrinking towards the moment it's switched on. The temperature climbs, the emptiness fills in. The gentle cold of deep space gives way to something warmer, then warm, then hot, then searing. Until, right at the edge, right at the limit of how far light has had time to travel, you arrive at a universe that is only a few 100,000 years old, practically a newborn, 13.8 billion years younger than the one you're lying in tonight. That's what the edge is. It's the most distant place you can see, and it's the youngest time you can see. And those turn out to be the very same place. The wall at the end of the sky is a wall made of the early universe itself, the cosmos as it was in its infancy, captured at one specific instant, glowing all the way around us in every direction. And that instant has a name. It's the moment the universe first became clear enough to see through. Before it, the universe was hiding behind a wall of fog so thick that no light could cross it. That fog is the real edge. It's the thing we actually run into when we look as far as looking can go. To understand what the edge is made of, you have to understand that fog, what it was, why it was there, and the single quiet event that finally lifted it and let the first light free. Because the light from that exact moment is still washing over you right now, tonight, from every direction at once. We just had to learn how to see it, So let's go back, all the way back, to the universe before it was clear. So go back to the universe in its first few 100,000 years. It looked nothing like the cosmos we know. There were no stars, no galaxies, no planets, no dust, no empty black space between things. There weren't even atoms, not finished ones. There was just heat and light and matter, all crushed together into a single substance that filled every corner of existence at once. That substance was plasma. And to understand the edge of the universe, you have to understand what plasma does to light. Take an ordinary atom, a heavy core in the middle, the nucleus and lightweight electrons drifting around it, held in place by their attraction to it. That's a normal finished atom, calm, neutral, balanced. The kind of thing you and everything around you is built from. But an atom is a fragile arrangement. Heat it enough and it falls apart. The electrons gain so much energy they tear loose from the nucleus and fly free. What you're left with is not atoms anymore. It's a churning mix of bare nuclei and loose electrons, all of it electrically charged, all of it moving at tremendous speed. That's plasma. It's what the inside of the sun is made of, and in the first few 100,000 years, it's what the entire universe was made of, everywhere, with no exceptions. Now, here's the crucial part. Light does not travel through plasma. Loose electrons are catastrophic for light. A photon, a particle of light, cannot get past a free electron. It runs straight into it, ricochets off in some random new direction, travels a tiny distance and slams into another one, and another, and another. The photon never gets anywhere. It's like trying to walk in a straight line across a packed room where everyone keeps shoving you sideways. You take a step, you get knocked off course. You take another step, you get knocked again. You burn enormous energy and you go nowhere. That's what light did in the early universe. It existed. In fact, the universe was drowning in light. Far brighter than anything today, but it was trapped. Every photon was caught in an endless, frantic pinball game off the free electrons packed into the plasma. It could not cross open space because there was no open space. There was only fog. You already know what this looks like in a smaller way. Think of a thick cloud lit by the sun. The cloud is bright. It can be blinding to look at, but you cannot see through it. The light isn't blocked. It's scattered. It bounces around between countless tiny water droplets so many times that all sense of direction is lost, and what reaches your eye is just a wall of featureless glow. You can't make out the sun behind it. You can't make out anything behind it. The cloud glows and it hides at the same time. The early universe was exactly that, on the largest possible scale. A glowing fog with no edges and no outside, filling all of space, blindingly bright and completely opaque. If you had been there, and you couldn't have been, but if you had, you would have been bathed in light from every direction, and you would have been able to see nothing at all. No distance, no shapes, just an even, searing brightness pressing in from everywhere, like being inside a furnace with no walls. There's an even closer example, and it's right above you in the daytime. the sun. The light you see from the sun's surface did not come from its core in any quick way. It was born in the nuclear furnace at the center, and then it spent an almost unimaginable amount of time, by some estimates tens of thousands of years, fighting its way out, scattering off one charged particle after another, random step after random step, until it finally reached the surface and broke free into space. The inside of the sun is opaque for the very same reason the early universe was: free electrons, trapped light, fog. So when we talk about the edge of the universe, this fog is what we're really talking about. This is the wall. When you look out into space, deeper and deeper, further and further back in time, you are moving toward this era. And when you reach it, you stop. Not because the universe ends there, it doesn't, but because the universe becomes opaque there. You hit the fog, and the fog will not let any light through from before it. There is a curtain drawn across the early universe, woven out of trapped light, and we cannot see a single thing behind it. Not with any telescope. Not ever, no matter how good our instruments get. Before this point, the universe simply did not allow light to travel, so there is no light from before it for us to catch. This is the deepest thing our eyes can ever reach, the oldest image the universe is willing to show us, and it is not a galaxy, or a star, or a first speck of matter. It is the surface of the fog itself, the last place the trapped light was. At the instant, everything changed, because the fog did not last forever. The universe was doing one thing the entire time, steadily, without pause. It was expanding, and expanding means cooling. And cooling, eventually, was about to perform a kind of miracle. It was about to make the entire universe transparent, everywhere, almost all at once. It was about to lift the fog and set the oldest light in existence free to fly in a single moment after hundreds of thousands of years of being trapped. That moment is the edge. Let's watch it happen. 380,000 years after the beginning. That's the moment. Hold that number for a second, because it's about to become one of the most important numbers in this whole story. 380,000 years. It sounds like a long time, and by human reckoning it is. It's longer than our species has existed. But against the age of the universe, it's nothing. If you shrank the entire 13.8 billion year life of the cosmos down into a single year, this whole event, the fog, the trapped light, the clearing, would all be over within the first 15 minutes of New Year's Day. Everything else, every star and galaxy and planet and living thing, comes in the remaining 365 days. The edge of the universe is something that happened in the cosmos's opening minutes. Here's what was happening. The universe had never stopped expanding, not for an instant. And as it expanded, that searing plasma was spreading thinner and cooling down, hotter to warm, warm to merely hot. The temperature had been falling the entire time, slowly, steadily, for the whole 380,000 years, and it was approaching a very particular threshold. That threshold is about 3,000 degrees, around 3000 Kelvin, roughly half the temperature of the surface of the Sun today. And something quiet and enormous happens when the universe finally cools below it. Below 3000 degrees, the electrons no longer have enough energy to stay free. That's the whole turning point. For hundreds of thousands of years, every time a nucleus tried to grab an electron and form an atom, the electron was moving too fast, carrying too much heat, and it simply tore loose again. The fog sustained itself, but as the temperature dropped past that line, the electrons finally slowed enough to be caught and held. The nuclei reached out, captured them, and would not let go. And all across the universe, for the first time, electrons and protons settled together into complete, neutral, finished atoms. Mostly hydrogen. The simplest atom there is, one proton, one electron, with a little helium mixed in. Scientists call this moment recombination. The name is a little misleading if you think about it too hard. The electrons and nuclei had never actually been combined before, so it wasn't a anything. But the word stuck, and it's what everyone uses. Recombination. The moment the universe pulled itself together into atoms. And the instant it happened, the fog lifted. This is the part worth slowing down for, because it's the heart of everything. Free electrons trap light. They're what made the universe opaque. But electrons bound up inside neutral atoms do not trap light the same way at all. They leave it alone. They let it pass. So the very moment those free electrons got captured and locked into hydrogen atoms, the thing that had been imprisoning light for hundreds of thousands of years simply vanished. The pinball machine switched off. The shoving crowd parted. And the light, all of it, the entire trapped ocean of ancient light that had been ricocheting in place since almost the beginning of time, was suddenly everywhere, free to fly. It had spent 380,000 years unable to travel more than a hair's breadth before being knocked off course. Now, in a relatively brief window, across the whole universe at once, the path in front of it opened up, and it shot outward in straight lines in every direction, and it has been traveling ever since, through the dark ages, past the births of the first stars, around and through the forming galaxies, for 13.8 billion years, almost without interruption. That light is still going. And here is the thing that should stop you for a moment tonight. Some of it is arriving right now. Some of it is reaching this exact point in space, this room, this moment, having left the surface of that clearing fog 13.8 billion years ago. It is the oldest light there is. Nothing older can exist because before it, light couldn't travel at all. We have a name for it, the cosmic microwave background, and it is quite literally what the edge of the universe is made of. When you look out as far as it's possible to look, this is the wall you hit. Not a wall of brick or rock or even of stars, but a wall of this ancient light. The flash of the moment the universe turned clear. Astronomers call that wall the surface of last scattering. It's a beautiful, precise name once you understand it. It is the surface marking the very last place each of those photons bounced, the final scatter of the final free electron just before that electron was captured and the fog let go. We are seeing the light from its last collision, frozen from 13 billion years away. So when someone asks what the edge of the universe is made of, this is the honest answer. It's made of light from the instant the cosmos became transparent. It's made of a single frozen moment, the surface of the primordial fire caught at the exact second it stopped being a furnace and became a clear, open sky. The edge is a photograph of the universe's first dawn, and we are still inside the flash. Now, one more strange and lovely thing before we move on, because it answers a question from the very beginning of tonight. Why does the edge sit the same distance away in every direction? Why are you at the center of it? Because the fog was everywhere. It didn't clear in one spot. It cleared all through space, all at once. So that final flash of light came from every direction around you, from above, below, and every side. And the light arriving at your eyes tonight after 13 billion years is the light that happened to start out at exactly the right distance to be reaching you now. That distance forms a sphere centered on you with you in the middle. It isn't that you're special. Everyone is in the middle of their own sphere. Every point in the universe sits at the center of its own edge, watching its own shell of ancient light arrive from all sides. The edge of the universe is not a place out there. It is a moment surrounding each of us, everywhere, all the time. Now let's talk about what that light actually looked like, because the name we gave it, the cosmic microwave background, quietly hides something beautiful. Microwaves are invisible. They're a kind of light, but far too low in energy for the eye to catch, the same family of waves your kitchen uses to heat a cup of water. So the name makes the edge sound like a faint, cold, colorless hum out at the limit of the sky. And today that's exactly what it is. But it was not born that way. At the moment the fog cleared, that light was not microwaves. It was glowing at about 3,000 degrees, and anything glowing at 3,000 degrees has a color you would recognize instantly. Think of the coil of an old electric stove as it warms up. Think of a bar of iron pulled from a forge. Think of the orange filament inside an old-fashioned light bulb, or the deep ember at the heart of a fire, or the color of certain cool, reddish stars. 3,000 degrees is the temperature of a warm, sullen, orange-red glow. So picture the universe at the instant of recombination, not dark, not empty. Glowing, softly, evenly, in every direction at once, the warm orange of a fading coal. The entire sky, everywhere, the whole cosmos, filled edge to edge with the color of a sunset. If you could have floated in that newborn universe and opened your eyes, you would not have seen stars because there were none yet. You would have seen no shapes at all. You would have seen a single, endless, gentle orange light wrapping around you completely, as though you were drifting inside an enormous warm lamp with no walls and no source, just glow. That is the true color of the edge of the universe, not black, orange, the soft orange of the first light. So here's the obvious question. If the edge is glowing warm orange, why don't we see it that way? Why, when we point our instruments at it, do we find not a warm orange fire, but a faint, freezing whisper of microwaves barely 2.5 degrees above the coldest temperature that can exist? Where did the fire go? It didn't go anywhere. It's still there. It's still glowing. We are just seeing it stretched. Remember the one thing the universe has been doing without pause this entire time: expanding. Space itself has been growing steadily for 13.8 billion years. And when light travels through space that is expanding, something happens to it. The space the light is moving through stretches out beneath it, and the light stretches with it. Its waves get pulled longer, the peaks spread further apart, and the length of a light wave is its color. Short waves are blue, longer waves are red. Longer still, and the light slides out of visible color entirely into infrared, the warmth you feel but cannot see. Longer still, and you reach microwaves. So as that ancient orange light flew toward us across 13 billion years, the expanding universe was stretching it the entire way. Orange to red, red to infrared, infrared finally all the way down to microwaves. The numbers here are clean and astonishing. The light has been stretched by a factor of about 1090. Its waves are roughly 1090 times longer now than the moment they were set free. And its temperature has dropped by exactly the same factor, from about 3000 degrees down to 2.7 degrees above absolute zero. The fire didn't burn out. It got pulled so long and so thin by the growth of the universe that it cooled to a cold the human body could never survive, and dimmed to a color the human eye can never see. But it is the same light that should land for a moment. The cold microwave hiss our instruments detect at the edge of the sky tonight is the very same glow that filled the universe at 3000 degrees, the same orange fire of the clearing fog, only stretched by the patient expansion of space across 13 billion years into a whisper. And there's a quiet consequence of this that touches everything, everywhere, including the room you're in. That stretched out ancient light didn't stay at the edge. It fills all of space. It's passing through you right now, faintly, from every direction. It sets the actual temperature of deep space, that famous figure of about 2.7 degrees above absolute zero, the cold of the void between the stars. That cold is not nothing. It's not the absence of warmth. It is warmth. The faint, leftover warmth of the edge of the universe, the dying heat of the first light, keeping the emptiest, darkest, coldest places in all of creation just barely, just slightly above absolute zero. The void is not truly cold, it's holding on to the last heat of the beginning. For almost all of human history, nobody knew the edge was there. We looked up at the night sky and saw stars and darkness, and the darkness between the stars looked like pure, empty nothing. The oldest light in the universe was washing over every person who ever lived, every night and every day, and not one of them could feel it or see it or had the faintest idea it was there. The first hint came not from a telescope, but from a piece of reasoning. In the 1940s, a physicist named George Gamow, working with his students Ralph Alpha and Robert Herman, followed the logic of a hot beginning to its conclusion. If the universe really did start out blazing hot and dense, they realized, then it should have left something behind. A glow, a bath of leftover light, cooled and stretched by billions of years of expansion until it had faded to just a few degrees above absolute zero, but still there, still filling all of space in every direction. They even estimated how cold it should be by now, and then, for the most part, the idea was set aside. It was a prediction with no way to test it, and the world moved on. For nearly 15 years, the edge of the universe sat in a few forgotten pages, waiting. It was found, in the end, completely by accident, by two men who were not looking for it and who spent the better part of a year trying to make it go away. The year was 1964. The place was Holmdel, New Jersey, at the Bell Telephone Laboratories. Two radio astronomers, Arno Penzias and Robert Wilson, had been given the use of a large, oddly shaped antenna, a giant metal horn built originally to bounce signals off the earliest communication satellites. They wanted to use it for careful astronomy, to measure faint radio signals from the sky. And to do that, they first had to account for every possible source of noise, so they could be sure that whatever they measured was real and not just interference. They wanted a perfectly quiet instrument. They could not get one. No matter where they pointed the antenna, there was a hiss, a faint, steady whisper of microwaves, very weak, but absolutely persistent. And it had a maddening quality. It was the same in every direction. It didn't matter where in the sky they aimed. It didn't matter what time of day it was or what season. The hiss was always there, always the same, coming from everywhere at once, completely even across the entire sky. By every rule they knew, that made no sense. Real sources in the sky come from somewhere. This came from nowhere, which meant everywhere. So they did what any careful scientist does. They assumed something was wrong with the equipment, and they set out to find it. They checked the wiring, they checked the electronics, they considered radio interference from nearby New York City and ruled it out. They considered whether it could be lingering fallout from nuclear weapons tests. And then they discovered that a pair of pigeons had taken up residence inside the antenna's horn and had coated the interior with droppings, which Penzias, rather memorably, described in the polite language of a technical report as a white dielectric material. Here was a culprit. They cleaned out the mess. They removed the pigeons. They scrubbed the antenna. The hiss stayed exactly where it was. What they didn't know, what they had no way of knowing, was that only about 60 kilometers away at Princeton University, another group of physicists had quietly re-derived Gamow's old prediction. A team led by Robert Dicke, with a brilliant young theorist named Jim Peebles, had worked out that the universe should be filled with this leftover glow, and they were, at that very moment, building an antenna of their own to go looking for it. They were about to hunt for the edge of the universe. They simply hadn't started yet. A phone call connected the two worlds. Penzias, increasingly puzzled by a hiss he couldn't explain, mentioned his problem to a colleague who mentioned the Princeton group, who had been talking about exactly this kind of signal. Penzias called Dicke, and as Dicke listened to this radio astronomer describe a faint, even microwave hiss coming uniformly from every part of the sky, he understood immediately what it was. He hung up the phone, turned to his team, and said, in effect, "We've been scooped," because Penzias and Wilson had found it. The thing they had spent a year trying to eliminate, the noise they had blamed on their wiring and their pigeons, was not a flaw in the antenna at all. It was the oldest light in existence. It was the glow of the clearing fog, the surface of last scattering, the cosmic microwave background arriving at their antenna from 13 billion years and 46 billion light years away from the edge of the universe in every direction at once, exactly as a forgotten prediction had said it would. They had pointed a metal horn at the sky to measure some quiet radio signals, and instead, they had accidentally heard the first light of creation. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for it, not for searching, for listening carefully to a noise they couldn't get rid of and being honest enough not to ignore it. And here is the detail that brings it all the way home into the ordinary world. For decades, almost every household had a way to see this same ancient light for themselves and never realized it. Old televisions, the analog kind, the ones that picked up broadcasts through the air. When they landed between channels on no station at all, they showed that restless black and white snow, static, random flickering dots, and a soft hiss of sound. And a small fraction of that snow, a faint sliver of it, was not coming from any broadcast tower or any electronic glitch. It was the cosmic microwave background. It was the edge of the universe, the light of the first dawn, picked up by an ordinary rooftop antenna and sprayed across a living room screen. People used to slap the side of the set to make the static go away. They were trying to get rid of the oldest light there is. Think about that the next time the idea of the edge of the universe feels impossibly far away and abstract. It isn't far away at all. It's arriving constantly, everywhere, through you and through everything. It was flickering in the corner of countless living rooms. The most distant thing it is possible to see has been quietly in the room with us the whole time. Once we knew the edge was there, the obvious next thing was to look at it closely, to map that faint glow across the entire sky and see what it had to tell us. And what it had to tell us turned out to be almost everything. Start with how smooth it is. When you measure the temperature of the cosmic microwave background in one direction and then in another and then in another, you get the same answer to an almost unbelievable precision. About 2.7 degrees everywhere, the same in every corner of the sky to within 1 part in 100,000. It is the most uniform, most featureless thing ever measured. If you smooth the surface of the ocean to the same evenness, the tallest wave on the entire planet would be a fraction of a millimeter high. That smoothness is itself a discovery. It tells us the early universe, the clearing fog, was extraordinarily even. Nearly the same temperature, nearly the same density, everywhere at once. The cosmos began not as a mess, but as something almost perfectly smooth and calm, but not quite perfectly. And the not quite is where it gets extraordinary. Buried in that smoothness, at the level of 1 part in 100,000, there are differences. Faint patches that are a hair warmer, faint patches a hair cooler. Ripples in the glow, far too subtle for any eye, detectable only by instruments built to split hairs 100,000 ways. For a long time, we knew they had to be there, but we couldn't see them. They were too faint. And then, slowly, with 3 remarkable machines, we learned to read them. The first was a satellite called COBE, launched in 1989. Its job was to measure the edge more carefully than anything before it, and it did 2 things that changed cosmology forever. First, it confirmed that the glow of the edge is an almost flawless match to the kind of light a hot object gives off as it cools. Exactly, precisely what you'd expect if the universe really did begin hot and dense and has been cooling ever since. It was perhaps the strongest evidence the hot Big Bang had ever received, and when the measurement was shown at a scientific meeting, the room reportedly broke into applause. And second, after painstaking analysis, COBE caught the ripples. For the first time, we had a map, blurry, coarse, low resolution, but real, of the faint, warm and cool patches across the edge of the universe. The first photograph of the infant cosmos. The scientists behind it later received a Nobel Prize. The second machine was WMAP, launched in 2001. Where COBE's map was blurry, WMAP's was sharp. It traced the pattern of those ripples in fine detail across the whole sky. And from that pattern, cosmologists could begin to calculate the exact texture of the warm and cool patches, how big they are, how they cluster, how strongly they vary, turns out to encode the deepest properties of the entire universe. From WMAP's map came one of the most important numbers in all of science, the age of the cosmos, pinned down for the first time to within a few percent. 13.7 billion years, it said, later refined to 13.8. That number from the very beginning of tonight, the age of the universe, is not a guess and never was. It was read directly off the pattern in the edge. The third machine was Planck, launched in 2009, and its map of the edge is the sharpest we have ever made. It measured the ancient light with such precision that the ripples came into focus as a detailed, intricate pattern covering the entire sky, the most complete portrait of the newborn universe ever assembled. And from that single image, cosmologists extracted the recipe of reality itself. Here is what the edge told us we are made of. Everything you have ever seen or touched, every star, Every planet, every living thing, every atom of every object in the known universe, all of the ordinary matter put together makes up only about 5% of what exists. About 27% is something else entirely, a substance we cannot see and have never directly held that gives off no light at all, known only by its gravity. We call it dark matter, which is really just a name for our ignorance. And the remaining 68%, the great majority of everything, is stranger still, a kind of energy woven into empty space itself, pushing the universe to expand faster and faster as time goes on. We call it dark energy, and we understand it even less. Sit with that for a moment. The familiar universe of stars and worlds and people is 5% of the total. The other 95% is two kinds of darkness we can barely describe. And we know this. We know the precise proportions, because they are written into the faint, warm and cool pattern on a wall of 13-billion-year-old light at the edge of the sky. We read the composition of the entire universe off its baby picture. And there's one more thing those ripples are, which is maybe the most moving of all. They are the seeds. Every one of those faint patches, slightly denser than its surroundings, carried slightly more gravity. And gravity, given enough time, is patient and relentless. Over millions and then billions of years, the slightly denser patches pulled in more matter and grew and pulled in more and grew until they collapsed into the first stars, the first galaxies, and eventually the vast cosmic web of galaxies and clusters and filaments that fills the universe today. Everything that exists grew from those tiny ripples in the edge, which means the faint pattern on that ancient wall is more than a baby picture of the universe. It's a blueprint. The slightly warmer speck in one direction became, over 13 billion years, a thread of 1,000 galaxies. Somewhere in that pattern is the seed that became our own galaxy, our own sun, our own world, and the atoms that became you. You can look at the edge of the universe and know that you began there as a faint ripple, one part in 100,000 warmer than the dark around it. The edge is the most distant thing we can see, and it is also the most informative thing there is, and the oldest family photograph we will ever have. We just said the ripples on the edge are the seeds of every galaxy. But we skipped past a question that deserves its own moment tonight. What actually made those ripples? Where did the pattern come from? And the answer is one of the most unexpected facts in all of science. The pattern on the edge of the universe is frozen sound. The early universe was filled with sound, and we can still see it. Go back into the fog one more time before recombination, when everything was that hot plasma of light and matter pressed together. That plasma had two things fighting inside it, constantly, everywhere. On one side, gravity. The faint, denser patches, the ripples, had a little more matter, and so a little more gravity, and gravity wanted to pull more matter in to make the dense spots denser. On the other side, the trapped light. All those photons caught in the fog were pushing outward with enormous pressure, and they resisted being squeezed. So, in every dense patch, the same struggle played out. Gravity pulled the matter in. The light pressure shoved it back out, in and out, squeeze and rebound. That is exactly what sound is. Sound is nothing more than a pattern of squeezing and rebounding, moving through a substance, compression and release, rippling outward as a wave. When gravity compressed the plasma and light pressure pushed it back, it sent pressure waves rolling through the early universe, real sound waves moving through the fog at more than half the speed of light. The whole cosmos was ringing. You couldn't have heard it. The waves were unimaginably vast and slow, single sound waves with wavelengths thousands of light years long, a tone so deep it falls more than 50 octaves below the lowest note any human ear could ever register. But it was sound in the truest physical sense. For 380,000 years, the entire universe was a single instrument ringing with a deep, vast tone, the same everywhere. And then the fog cleared, and in that moment the sound froze. When recombination happened and the light broke free, the pressure that drove the waves vanished, the photons flew away, and the push and rebound stopped instantly everywhere. Whatever the wave pattern looked like at that exact instant got locked in place. The compression stayed as slightly denser, slightly hotter patches. The rebound stayed as slightly thinner, cooler ones. The sound of the early universe stopped being a sound and became a still photograph, printed onto the edge, where it has stayed for 13 billion years. So when we look at the faint, warm and cool ripples in the cosmic microwave background, we are not looking at random texture at all. We are looking at a single frozen frame of the sound that filled the universe at the moment it fell silent. We are seeing music with our eyes, stopped mid-note. And the frozen note has a very particular size which turns out to be one of the most useful measurements in all of cosmology. The warm and cool patches have a characteristic scale. They're typically about 1 degree across on the sky, roughly twice the width of the full moon. That size is set by a simple thing: how far sound could travel through the plasma in the 380,000 years before the fog cleared. The waves had exactly that long to spread, and no longer. So the pattern they left has a built-in, fixed length, a kind of cosmic yardstick stamped identically across the entire sky. Astronomers call it the sound horizon, and it's become one of our most precise tools. Because we know the real physical size of that frozen ripple, we can compare it to how big it looks from here and use the difference to measure the shape of space, the distance to the edge, and the rate at which the universe is expanding. The same frozen sound even shows up much closer to home. Galaxies across the universe are very slightly more likely to sit about 500 million light-years apart than any other distance. A faint preference, echoing the exact scale of those primordial sound waves written into the spacing of galaxies themselves. The note the early universe rang has been hanging in the structure of the cosmos ever since, and we measure the universe by it. Scientists have even taken the real frequencies of that primordial sound, far too deep to hear, and shifted them up octave after octave, into the range of human hearing, so you can listen to a simulation of what the universe sounded like in its first minutes. It's a deep, resonant tone, a little like a low hum, and it slowly falls in pitch as the cosmos expands and the instrument grows larger. The first sound. The only sound there was when there was nothing yet to hear it. And it's still there, frozen on the edge, waiting in the pattern of the oldest light. Now I want to come back to the smoothness of the edge, because we passed over it quickly, and it hides one of the deepest puzzles in cosmology, and one of the strangest ideas physics has ever taken seriously to solve it. Remember how even the edge is the same temperature in every direction to 1 part in 100,000. That sounds like a tidy fact. It's actually almost impossible. And here's why. Look at one edge of the sky in one direction. Now look at the opposite edge in the exact opposite direction. Both are about 46 billion light years away. Their light is only just now reaching you after traveling the entire age of the universe, which means those two patches of sky have never, in the whole history of the cosmos, been in contact with each other. Light from one could not possibly have reached the other. There hasn't been enough time, not even close. They are, in the language of physics, completely cut off. Two regions that have never exchanged anything, never touched, never shared a single particle of light. So why are they the same temperature? Sit with how strange that is. 2 cups of coffee on opposite sides of the world will not be at the same temperature unless something connected them, unless they were poured from the same pot or left to settle in the same room. Things only even out to a shared temperature if they can reach each other and exchange heat. But these two opposite edges of the universe have never been able to reach each other at all. And yet they match, not roughly, but to 5 decimal places. Every far-flung region of the sky, none of them ever in contact, all somehow agreeing on the same temperature to 1 part in 100,000. By the ordinary rules, that should be flatly impossible. It's called the horizon problem, and for years it sat there as a genuine crack in our understanding of the beginning. The leading answer is an idea called inflation, and it is audacious. It says that in the very first sliver of the first second, within something like a trillionth of a trillionth of a trillionth of a second after the beginning, the universe went through a burst of expansion unlike anything before or since. In that unimaginably brief instant, space stretched by a factor of at least 100 trillion trillion. A patch smaller than a single atom was blown up to something larger than a grapefruit, and the expansion was so violent that space itself grew far faster than the speed of light. That last part sounds like it breaks the rules, but it doesn't. Nothing was moving through space faster than light. Space itself was expanding, and space is allowed to do that. There's no speed limit on the stretching of the fabric itself, only on things traveling through it. And inflation solves the impossible smoothness in one stroke. Before that burst, the entire region that would become our observable universe was a tiny, tiny patch, small enough that every part of it was in easy contact with every other part. close enough to settle to a single shared temperature, the way coffee in one cup does. It evened itself out completely while it was still small. And then inflation took that tiny, already uniform patch and blew it up to a colossal size in an instant, carrying the sameness along with it, flinging matched regions to opposite ends of the sky. The opposite edges of the universe agree on their temperature because long ago, before inflation, they were touching. They were neighbors in a patch smaller than an atom before being thrown billions of light years apart. The smoothness of the edge is the fingerprint of that first tiny patch stretched across everything. And inflation does one more thing which closes a loop from earlier and is maybe the most staggering idea of the whole night. It explains where the ripples came from. At that subatomic scale, before the stretching, the patch was subject to the unavoidable jitter of the quantum world, the tiny, restless flickers in energy that the rules of physics say can never be fully smoothed away, even in empty space. Inflation took those microscopic quantum flickers and stretched them too, blowing them up from subatomic size to cosmic size, freezing them in as the faint, denser and thinner patches in the new, enormous universe. The ripples, the seeds, the same ones that became sound, and then galaxies, and then us. Which means the largest structures in all of existence, the great walls and superclusters of galaxies stretching across hundreds of millions of light years, began as the smallest things there are. Quantum flickers in a patch smaller than an atom, magnified in an instant to the size of the sky. When you look at the pattern on the edge of the universe, you are looking at quantum noise from the first fraction of the first second, written across the heavens and grown over 13 billion years into everything. There's one more thing hidden in the edge, and unlike everything else tonight, this one isn't about the early universe at all. It's about you, and where you are and how fast you're really moving, which is not what you think. We keep saying the edge is the same temperature in every direction to 1 part in 100,000. That's true of the faint ripples. But there's one deviation in the cosmic microwave background that's much larger than all the rest, about 100 times bigger than the ripples. It's not a speckled pattern, it's a single, smooth, lopsided gradient across the whole sky. One entire half of the sky is slightly warmer. The opposite half is slightly cooler. A gentle, warm glow in one direction, fading evenly to a cool one in the other. For a while, this was puzzling, until people realized what it was. It isn't a feature of the early universe, it's a feature of our own movement. We are moving through the bath of ancient light, and the gradient is the wake of that motion. You already know the everyday version of this. When an ambulance races toward you, its siren sounds higher. As it passes and races away, the pitch drops. The sound waves ahead of it get squeezed shorter and higher. The ones behind get stretched longer and lower. Light does the same thing. As we move through the sea of first light, the light in the direction we're heading gets very slightly squeezed, shifted warmer. The light behind us gets very slightly stretched, shifted cooler. So one half of the edge looks a touch warmer, simply because we are rushing toward it. And from the exact size of that warm-cool gradient, we can read our own speed. It turns out to be about 370 kilometers per second. The Earth, the Sun, the entire solar system is sailing through the oldest light in the universe at 370 kilometers every second, roughly in the direction of the constellation Leo, not 370 kilometers an hour per second. While you lie here feeling perfectly still, you are moving against the first light faster than any spacecraft humanity has ever built. But here's the part worth holding on to, the quietly profound part. The edge gives the universe a frame of rest. There is one particular state of motion, one specific velocity, in which the ancient light looks exactly the same in every direction, with no warm side and no cool side, perfectly balanced. That's the frame at rest with respect to the universe as a whole, the average motion of all the matter and light there is. And against that frame, your motion is not a matter of opinion. It's real, it's measurable, it's an actual number. Your true speed relative to the universe itself, relative to the moment of the beginning. We spend our lives with no sense of absolute motion. On a smooth flight, you can feel utterly still while crossing the sky at the speed of sound. There's normally no way to point and say how fast you're really going, with no landmarks, because motion is relative. There's no fixed post to measure against. The edge of the universe is the closest thing there is to that fixed post. It's the one backdrop the whole cosmos shares, and it tells you quietly from every direction at once that you have never once been still, not for a single second of your life. You have always been moving through the first light, and the first light has been keeping the record. We've spent all night treating the edge as the end, the farthest wall, the oldest light, the limit of sight. But for the universe itself, that moment was not an ending at all. It was a beginning. It was the morning of everything that came after. So before we drift home, let's step over the edge, just briefly, and follow time forward to see what the universe did once the fog had cleared and the first light was set free. At first, not much. The instant the fog lifted, the universe was filled with that warm orange glow and a thin, smooth sea of the simplest matter there is, neutral hydrogen and a little helium, spread almost evenly through all of space. There were no stars, no galaxies, just gas and fading light. And as the universe kept expanding, that orange glow stretched and dimmed, exactly as we described, orange to red, red to infrared, and then, finally, out of visible light altogether, and the universe went dark. This is a part of the story that often gets skipped, and it's one of the strangest chapters of all. After the brilliance of the early universe faded, there was nothing left to shine. No stars had formed yet. The afterglow had reddened into invisibility. And so the cosmos entered a long, total darkness, a universe of cold, dark, silent hydrogen gas, with no source of light anywhere in it, drifting and slowly gathering under gravity. Astronomers call it the cosmic dark ages. It lasted somewhere between 100 and a few 100 million years. The longest, deepest night there has ever been or ever will be, a universe waiting in the dark for its first star. But the seeds were already working. Quietly, invisibly, gravity kept doing the one thing it always does. In the slightly denser ripples, the frozen sound, the stretched quantum flickers, the hydrogen gas was being pulled together, gathering, thickening, collapsing inward. The clumps grew denser and hotter at their centers, century after century, for tens of millions of years, squeezing tighter, heating up, until somewhere around 100 to 200 million years after the beginning, in the heart of one of those collapsing clouds, the pressure and heat crossed a threshold, and a core of hydrogen caught fire into nuclear fusion. A star. The first star. The first new light in the universe since the edge. After the longest night, the cosmic dawn. And the first stars were monsters, nothing like the stars of today. Because they formed from pure hydrogen and helium, with none of the heavier elements that change how a star burns, they could grow to enormous sizes, many times the mass of our sun, blazing furiously hot and brilliant blue, burning through their fuel in just a few million years, and then dying in tremendous explosions. And in their cores and in those death explosions, they did something the universe had never done before. They forged the first heavy elements, the first carbon, the first oxygen, the first iron. Every atom heavier than hydrogen and helium that exists today, the carbon in your cells, the oxygen in your breath, the iron in your blood, was first made in those early stars and scattered into space when they died, to be gathered into the next generation and the next, and eventually into a quiet world orbiting an ordinary star, and into you. The first stars changed the universe in one more way. Their fierce ultraviolet light reached out into the surrounding hydrogen and tore the electrons back off the atoms, undoing recombination in reverse in growing bubbles of charged gas around each cluster of new stars. Those bubbles spread and overlapped and merged until, by about 1 billion years after the beginning, nearly all the hydrogen between the galaxies had been lit up and broken apart again, and the universe became fully, permanently transparent the way it is today. This era, the first stars, the first galaxies emerging out of the dark ages, is the exact frontier the James Webb Space Telescope was built to reach when it stares at the faintest, most distant smudges of light it can find. It is looking for the cosmic dawn, the first lights coming on just over the edge. So the edge is not really a wall at the end of everything. It's a doorway at the beginning of everything. On our side of it, 13 billion years of stars and galaxies and worlds. On the far side, the dark, and then the first dawn. And the oldest light we can see is the light from the threshold between them, still arriving, still glowing, marking the line between the universe that was dark and the universe that learned to shine. Let's come back now to the light itself and to a question we've been quietly leaning on all night without answering. How do we actually know that the faint hiss at the edge is the afterglow of the beginning? Penzias and Wilson found a uniform microwave glow coming from everywhere. That's striking, but on its own it doesn't prove where it came from. So what makes us so sure this is the cooled fire of the early universe and not some other source, scattered starlight, dust, the combined hum of distant galaxies? The proof is hidden in the exact shades of the glow, in its spectrum. Here's the idea. Take any glowing object and spread its light out by wavelength. Measure how much it gives off at each color, from the reds through to the blues and beyond. What you get is a curve, a particular distribution of colors, and for anything glowing simply because it's hot, a coal, a star, a bar of iron pulled from a forge, that curve has a very specific, very recognizable shape, fixed entirely by one number, the object's temperature. Physicists call it a black body curve. It is one of the most dependable signatures in all of physics. Tell me the temperature, and I can draw you the exact curve. Show me the exact curve, and I can read you the temperature and tell you that this light came from something simply hot and cooling. So, here was the test. If the cosmic microwave background really is the leftover heat of a hot, dense, early universe that has been cooling for 13 billion years, then it should glow as a near-perfect blackbody, a flawless curve at one single temperature across the whole sky. And if it came from anything else, many different sources, scattered and overlapping, it almost certainly would not. The curve would be lumpy, or skewed, or wrong. In the early 1990s, the COBE satellite carried an instrument built to measure that curve with extraordinary care. And the result it returned is, to this day, one of the most beautiful measurements in the history of science. The light from the edge traced out a blackbody curve so perfect that it is, in fact, the most perfect blackbody ever measured anywhere. More perfect than anything we can manufacture in a laboratory, more perfect than the glow of any star or furnace we have ever studied. When the team plotted their data against the theoretical curve, the measured points fell on the line so exactly that the little error bars marking the uncertainty were smaller than the width of the line itself. There was, visibly, nothing to argue with. When that plot was shown at a meeting of astronomers, the room reportedly rose to its feet. That single curve is one of the firmest pieces of evidence the hot Big Bang has. Because there is essentially only one thing in nature that produces a black body glow, that perfect, that smooth, that uniform across the entire sky. Light that was once in complete balance with hot, dense matter and has been cooling ever since. The edge glows exactly like the cooling embers of a fire that once filled all of space, at a temperature now measured to be 2.725 degrees above absolute zero, pinned down to within a fraction of a thousandth of a degree. So when we speak about the edge with such confidence, its temperature, its age, what it's made of, it's not guesswork, and it's not a blurry smudge we're squinting at. It is the single most precisely measured light in the universe. We know the temperature of the oldest thing we can see more exactly than we know the temperature of almost anything here on Earth. And even the perfect glow and the frozen ripples are not the last thing written into the edge. There's a third layer, fainter than either, that we've only recently learned to read, and it may carry the most astonishing message of all. The ancient light is very slightly polarized. Polarization is a subtle property of light. It has to do with the orientation of the light waves, the direction in which they vibrate as they travel. Ordinary light from most sources is a jumble of every orientation at once. But when light scatters off matter in a particular geometry, it can come away with a faint preferred direction, a slight alignment. And in the last moments before the fog cleared, as the ancient light made its final scatters off the last free electrons, it picked up exactly that, a faint, patterned polarization woven in at the surface of last scattering and frozen there ever since. Mapping that polarization gives us a whole second layer of information beneath the warm and cool ripples. It independently confirms the story of the sound waves and sharpens nearly every number we draw from the edge. That alone would make it worth the enormous effort it takes to measure. But it's not why teams of scientists have spent years in the most hostile places on Earth chasing it. They're chasing one specific pattern hidden in that polarization. Because if it's there, it would be the closest thing imaginable to a photograph of the first instant. Think back to inflation, that violent burst of expansion in the first sliver of the first second. If it really happened, it should have done more than stretch quantum flickers into the seeds of galaxies. It should have shaken the fabric of space itself, sending out gravitational waves, ripples in space-time, spreading from the moment of inflation. And those primordial ripples passing through the plasma in the moments before the fog cleared would have twisted the polarization of the ancient light into a faint, distinctive swirl, a kind of handedness, a curl that the ordinary density ripples simply cannot produce. Finding that swirl in the edge would be like catching the tremor of the universe's first fraction of a second frozen into the oldest light. It would be a direct fingerprint of inflation itself, a glimpse of the beginning's beginning. The hunt for it is one of the great quiet dramas of modern science. In 2014, a team running a telescope at the South Pole announced that they had found it. The swirl, the signature of inflation. And for a few electric weeks, it looked like one of the discoveries of the century. Then, a more careful analysis showed that most of what they had seen could be explained by dust in our own galaxy. Faint grains aligned by magnetic fields, mimicking the very pattern they were looking for. It was a caution, not a triumph. The signal of the first instant, if it's there at all, is even fainter than they had hoped, and still buried somewhere beneath the foreground glow of the Milky Way. And so the search goes on, with ever more sensitive instruments in the cold, clear air at the bottom of the world, all of them staring at the edge, waiting for the twist. If we ever do find it, we'll have done something that sounds impossible. We'll have reached past the surface of last scattering, past the wall of light itself, and read in the faint curl of the oldest light the signature of the moment the universe began to expand. The edge would have shown us not just its own face, but the instant before it was born. There's a promise I made at the very start of tonight that I haven't kept yet, and now's the time because we finally have everything we need to make sense of it. I told you the edge sits about 46 billion light years away in every direction. And if you were listening closely, that number should have bothered you because the universe is only 13.8 billion years old. Light travels 1 light year per year, no faster. So in the entire history of the universe, light can only have crossed 13.8 billion light years. How then can the edge be 46 billion light years away? How can we possibly see something 3 times farther than light could have traveled in all of time? It sounds like a flat contradiction. It sounds impossible. The answer is the one thread that has run through this whole night: expansion. Space itself has been stretching the entire time, and that changes what distance even means. Let's follow the actual light that's arriving tonight. When it left the surface of last scattering 13.8 billion years ago, the patch of universe that emitted it was not far away at all. Back then, everything was packed close together. The observable universe was thousands of times smaller than it is now. The matter that sent us this light was, at the moment it let go, only about 40 million light years away. Close, by cosmic standards, practically next door. Then the light began its journey toward us, and for 13 billion years it crawled across space at its fixed speed. But the whole time it traveled, the space it was moving through kept stretching, and the stretching carried its starting point farther and farther behind it. The light was swimming toward us through a river that was lengthening beneath it. So even as the light made progress, the place it came from was being swept away in the other direction. By now, that original patch of matter, the stuff that emitted the light landing in your eyes tonight, has been carried all the way out to about 46 billion light years away. It didn't travel there. It was carried there by the expansion of space itself. So the same edge has 3 different distances at once, and all 3 are true. The light traveled for 13.8 billion years. It set out from a place that was about 40 million light years away at the time, and that place is now about 46 billion light years away. There's no single number for the distance to the edge because in an expanding universe, distance isn't one thing. It depends on whether you mean then or now or how long the light was in flight. The contradiction was never real. It was just the assumption that space stands still while light crosses it, and space has never once stood still. This stretches the whole observable universe out to a span that defies the simple arithmetic. About 93 billion light years across, edge to edge, in a cosmos only 13.8 billion years old. And inside that sphere, by our best counts, there are something like 2 trillion galaxies. 2 trillion. Each one a city of 100 billion stars or more. All of them inside the part we can see. all of it grown from those faint ripples on the edge, all of it carried apart over 13 billion years by the same patient expansion that stretched the first light from orange fire into a cold microwave whisper. And there's a gentle sorrow folded into this, the same one we touched earlier. The patch of matter that sent us tonight's ancient light is not a glowing fog anymore. 13 billion years have passed there too. Whatever it became, galaxies, stars, perhaps worlds, has lived out the same long history our own corner has, but we will never see it. Its light from now, from today, is being carried away from us faster than it can cross the growing gap, and it will never arrive. We see that distant place only as it was at the very beginning, as the edge, as the first light. Its present is forever beyond our reach. We get its infancy, frozen and glowing, and nothing after, so we've reached the edge, the surface of last scattering. The oldest light there is, the wall of the clearing fog, 380,000 years after the beginning. And a natural question settles in. Is that truly the final wall? Is there genuinely nothing beyond it, or is it only the last thing we happen to be able to see? With light, it is final. Let's be clear about that, because it's a real and permanent limit. We will never see a single particle of light from before recombination, no matter how good our telescopes become, not in 1,000 years, not in 1,000,000. The fog is an absolute curtain for light. Before that moment, light could not travel, so there is no earlier light to catch. The edge made of the cosmic microwave background is, for the eye and for the telescope, the end of the road. It is the oldest image that can possibly exist. But light is not the only messenger the universe has. There are, in principle, two ways to reach behind the wall, two faint signals that escaped the early universe even earlier than light did, and that are, in theory, still out there, even older echoes waiting to be heard. The first is neutrinos. Neutrinos are ghost particles, almost nothing at all, with no electric charge and almost no mass, so reluctant to interact with ordinary matter that trillions of them are passing through your body every second without touching a single atom of you. And because they interact so weakly, they stopped being trapped by the early universe far sooner than light did. While light was still caught in the fog at 380,000 years, neutrinos had already broken free at around 1 second after the beginning. 1 second. There should be, filling all of space right now, a cosmic neutrino background, a sea of these ghost particles, even older than the light at the edge, a wall standing behind the wall. We have not caught it directly yet. Neutrinos are agonizingly hard to detect for the very same reason they escaped so early. But it is almost certainly there. An older edge we can feel the weight of, but not yet see. The second messenger is stranger still. Gravitational waves, ripples in the fabric of space itself, set off by violent events and spreading outward at the speed of light. Unlike light, gravitational waves pass through everything. The fog could not have stopped them. So ripples from the very first instance of the universe, from before there was any light free to travel, from almost the moment of the beginning itself, could in principle still be washing through the cosmos today, carrying a signal from an edge far older than the one we can see. We have only just learned to detect gravitational waves at all, from enormous nearby events like black holes colliding. Catching the faint primordial ones from the dawn of time is beyond us for now. But if we ever do, we will be looking past the wall of light, almost all the way back to zero. So the edge of light is not quite the edge of everything. There are older walls behind it, woven from ghostlier things that we may someday learn to read. Now, the other question. What about space beyond the horizon? The regions so far away their light simply hasn't reached us yet. What's out there? Almost certainly more of the same. More galaxies, more stars, more vast and quiet structure, stretching on. There is nothing special about the edge of our observable bubble. It's not a wall in the real universe, only the limit of how far light has had time to travel to us. Cross it, and you'd find an ordinary patch of cosmos that considers itself the center of its own bubble, with its own edge 46 billion light-years away in every direction. And beyond that, more still. The true universe is far larger than the part we can see. It may well be infinite. We are not near its center, because in an endless universe there is no center. We are simply at the middle of our own little sphere of visibility, and so is every other point in existence, each one alone inside its own horizon. And here is the last thing about the edge, the thing that gives it a kind of quiet weight. The edge is moving, and it's moving in two directions at once. In one sense, it's slowly growing. With every year that passes, light from a little farther away finally has time to complete its journey and reach us, so the horizon creeps outward, and the observable universe gently widens. New things drift into view, but expansion is doing something to the edge as well, and this is the haunting part. The expansion is accelerating. It's speeding up, driven by that dark energy we barely understand. And as it accelerates, the most distant galaxies are being carried away from us faster and faster. There comes a point, for each of them, where the space between us is growing faster than their light can cross it. And when a galaxy passes that threshold, its light can never reach us again. It redshifts and dims and fades and is gone. Not destroyed, just carried forever beyond reach, sealed off on the far side of a horizon that's closing. Over the long future of the cosmos, billions of years from now, one by one, the galaxies will slip away into the dark, until a future astronomer looking out might see almost nothing beyond their own local group of stars. An empty sky, with no sign that the wider universe was ever there. And the edge itself, the cosmic microwave background, will fade too. The same expansion that cooled it from 3,000 degrees to 2.7 will keep stretching it colder, longer, fainter, until one far day it is stretched so thin that no instrument could ever pick it out from nothing. The first light will still be traveling. It will simply have become too faint to find. There will be a time when the edge of the universe can no longer be read at all, when the oldest light has dimmed past detection, and any beings alive then will have no way to know the universe ever had a beginning or a glowing fog or an edge. Which means something quietly remarkable about right now. We are living in the window. The first light is still arriving, still just warm enough to catch. The pattern is still sharp enough to read. The edge is still there to be found, glowing faintly in every direction, telling anyone who learns how to listen exactly where everything came from. That window opened long before us, and it will close long after. But it is open now, and we are among the first who ever knew how to look through it. We've spent tonight talking about the edge of the universe as the most distant thing there is. 46 billion light years away, the oldest light, the farthest wall, and all of that is true. But there's a way of seeing it that turns the whole picture inside out, and it's the part I want you to carry with you as you drift off. The edge of the universe is not far away. It is here. It is in this room. It is passing through you right now as you breathe. Remember what the cosmic microwave background actually is. It's not a distant object sitting out at the boundary of the sky like a star you could point to. It's a sea of ancient light that fills all of space, every cubic inch of it, everywhere, including the space your body is occupying at this moment. That light has been flying freely since the fog cleared in every direction through everything. And it never stopped. So it is not only out there at the edge, it is also right here, streaming through the air around you, through the walls, through the bed, through your skin. Let's put a number on it, because the number is extraordinary. In every single cubic centimeter of space, a volume about the size of the tip of your finger, there are, on average, around 400 photons of this ancient light. 400 particles of the first dawn in a space the size of a fingertip, and they're moving at the speed of light, which means they are pouring through you constantly in unimaginable quantities. Billions upon billions of these 13-billion-year-old photons pass through your body every second of your life. They have been doing it since before you were born. They are doing it now. Most of them go straight through you, the way the neutrinos do, and continue on their way without ever noticing you were there. But not all of them. Every so often, one of these photons, one specific particle of light that broke free from the surface of last scattering 13.8 billion years ago, completes its journey by striking you, your skin, your closed eyelids. It is absorbed, and in that instant, after crossing almost the entire span of cosmic time and an unthinkable distance of expanding space, its journey simply ends. In you, in the dark, tonight. Think about the life of a single one of those photons. It was born in the fire, when the universe was a glowing fog, hotter than the surface of most stars. It spent the first stretch of its existence trapped, ricocheting endlessly off free electrons, unable to travel even a thread's width without being thrown back. Then, in the great clearing, the fog lifted around it and it was set loose, and it began to fly. And it flew. It crossed the cosmic dark ages when there was nothing to see. It passed the first stars as they ignited. It threaded between forming galaxies. It rode through expanding space for 13.8 billion years. Its color stretching from orange fire to invisible microwave, its temperature falling from 3,000 degrees to a few degrees above absolute zero. It crossed a distance the human mind genuinely cannot hold, and the very last thing that ever happened to it, the final event in a journey that began at the dawn of everything, was that it arrived in a quiet, dark room and was gently absorbed by a person lying still at the end of an ordinary day. That happens. It is not a metaphor. It is a real physical fact about where you are and what is around you. The edge of the universe is not a thing you only look toward. It is a thing that arrives, that ends constantly, harmlessly in you. And it's worth pausing on what that makes you in the simplest physical terms. You are sitting at the center of a sphere of the oldest light in existence, with that light arriving from every direction at once and passing through you without pause. You are, right now, in direct physical contact with the first moment the universe became clear. Not looking at a picture of it, touching it. The same event we trace to the very beginning of the cosmos is reaching across all of time to brush against your skin in the dark, billions of times a second, and has been your whole life, and you never felt a thing. There's something else hidden in this, and it closes a loop from earlier. Remember that the faint ripples in this same light were the seeds, the slightly denser patches that grew over billions of years into galaxies and stars and worlds, and eventually into the atoms that make up your body. So the edge of the universe is not only touching you from the outside, arriving as light, it is also what you came from. The hydrogen in the water in your cells was forged in that early universe. The pattern that decided a galaxy would form here, and a star within it, and a planet around that star, was written into the very wall of light that is now washing over you. You are made of the early universe, and you are bathed in the light of the early universe at the same time. You are the edge of the universe, folded up and grown complicated enough to look back out at where it began. So, the next time you read that the edge of the universe is impossibly far away, 46 billion light years, a distance past all imagining, you can know that the number, while true, hides the gentler truth underneath it. The edge is also the most intimate thing there is. It is closer to you than the far side of the room. It is on your skin. The first light never stopped arriving, and tonight, as you lie here, some of it is finishing its 13 billion year journey in the warmth of you and going no further. Now, as we come to the end of tonight, let's drift back from the edge slowly and take in what we've actually found out there. We went looking for a wall, a boundary, a place where the universe stops and something else begins. And we found that the edge isn't a place at all. It's a moment. The moment 380,000 years after the beginning, when a glowing fog that had filled all of existence finally cooled and cleared and let the first light fly. We found that the material at the end of everything is that light still arriving, stretched by 13 billion years of expanding space from warm orange fire into a faint cold whisper of microwaves. We found that the edge has a temperature and a color it used to be, and a faint pattern of ripples that turned out to be the blueprint for every galaxy that would ever exist. And we found that it is not far away and untouchable at all, but here, in the room, on your skin, finishing its journey in you tonight. And maybe that's the quietest, strangest thing about the edge of the universe. For 13 billion years, that light traveled toward this moment, and no one knew. It washed over the empty earth before there was life. It washed over the first creatures in the sea, who had no eyes to catch it. It washed over every human being who ever lived, every night of every life, completely unfelt and unsuspected, the oldest light there is pouring through them, ignored for the entire span of our species until the last sliver of a single century. Think about how recent our knowing is. The light is 13.8 billion years old. We have known what it is for about 60 years. For all but the final blink of human history, the first light arrived in total secrecy. It was already on its way when the first fish crawled onto land. It was already on its way when the dinosaurs lived and died. It was already on its way when the first human looked up at the night sky and wondered what the darkness was. It was already on its way through every century of every civilization that ever rose and fell, never once detected, never once understood. And then, in a single ordinary lifetime, a species of curious creatures on one small world built a metal horn and pointed it at the sky and finally heard the hiss that had been there all along and understood for the first time in the history of life on Earth that they were sitting inside the afterglow of the beginning of everything. That's the part worth holding on to. The universe did not hide its edge from us out of cruelty. It was never hidden at all. It was always here, always arriving, always glowing faintly in every direction, patient, waiting for something in the cosmos to grow complex enough and curious enough to notice. And against all odds, something did. We are the part of the universe that learned to feel its own first light. We are the edge of the universe, grown old enough and strange enough to look back across all of time and recognize where it came from. Thank you for spending this time with me tonight, drifting all the way out to the edge of everything and back. If these slow journeys through the cosmos help quiet your mind and carry you towards sleep, take a moment to subscribe and follow along so we can keep wandering out to places like this together. It genuinely helps these long, quiet nights continue. So as you let yourself settle now and your thoughts begin to slow, you don't need to picture anything far away. You don't need to reach for the edge of the universe. It's already here. It's in the dark around you, soft and even and everywhere, the same gentle glow that filled the whole young cosmos before there were stars, 400 particles of the first light in every fingertip of space, billions of them passing through you with every breath, finishing journeys that began at the dawn of time, ending quietly in the warmth of you. The edge of the universe is not a cold wall at the end of the dark. It's the oldest light there is, still arriving, still glowing, still reaching gently across 13 billion years to touch you right where you are. Rest now. The first light has you surrounded. Sleep well.